The intro to calculus video that you watched a couple weeks ago had talked about how calculus was developed out of a need to answer some bigger questions. For example, how to find the area of a figure that has curved sides, like a circle or any kind of figure that has curved sides. That idea of finding the area of any kind of region, and also finding a slope of a tangent line. Those are the two big ideas that really calculus has developed out of. And for pretty much the rest of the next couple of units, we're going to be talking about the second issue there, which is finding the slope of a curve. Okay, now we've already looked at derivatives. We know that a derivative is the slope of the tangent line, which is also the slope of a curve at a specific point. But that idea comes from the fact that on some curve, so let's say we have a generic curve, if we have a point, and if we can zoom in close enough on this point, then the curve will appear to be straight on an interval. Okay, and you can try this on a calculator. You could just graph like y equals x squared. We know that that's not linear, but if you zoom in super close on x equals 2 on that point at 2, 4, eventually everything on your screen is going to appear linear because you've zoomed in close enough. So that's called local linearity, and that is where our idea of the slope of a curve at a point, or the slope of the tangent line to a curve at a point, comes from. So what we're going to do today is look at I look at how we develop an algebraic definition for the derivative. Now, we already have seen plenty of examples of, if we're looking at a graph of f prime, what does that tell us about the behavior of f, or vice versa? But now we want to start looking at things more algebraically, since we have a better understanding of what they do graphically. Okay, so on here, we have a curve, and it's just a generic curve, happens to be polynomial, but this applies for any type of curve. And we also have a point C here. Now, real quick with variables, we're going to see variables that are constant and variables that are varying, all right, which seems a little counterintuitive, but the difference is, if you think about like in the formula for slope-intercept for a line, y equals mx plus b. Well, y, m, x, and b are all variables. They're all letters used in algebra to represent a number. However, for a specific line, m and b have a constant value, whereas y and x are still changing because it is a function y in terms of x. Same kind of idea here. The value c is actually a constant, meaning it is at a specific point. Now, could that point be somewhere else? Yes, but the point is the idea is that that point is not moving right now. So c is a constant. Okay, it's an x value on this curve's domain, and then f of c is the output, and that ordered pair is point P. Now, we have a tangent segment that's already drawn in here, okay? And according to this, the slope of that tangent line is 0.602. I could move this, and that would change, okay? Because we know that this is a curve. It doesn't have the same slope everywhere, but for now, we're just gonna leave it right here. Okay, so we know from pre-algebra, algebra 1 concepts that to find the slope of a line, we need two ordered pairs, and then we find the difference between the y's over the difference between the x's, okay? Rise over run is familiar to you. Change in y over change in x is familiar to you. y2 minus y1 over x2 minus x1, all of those you've heard plenty of times. In all of those situations, to find the slope, we need a second point. So the first thing we're going to do is we are going to put a second point on here, okay? Now, program moves a little slow. Okay, so we have this second point, okay? And we are going to call the x value, instead of using like x1 and x2, since we've already labeled this as c, we're going to call this second point c plus h. And the reason we're calling it c plus h instead of using another letter like d is we are going to describe this point in terms of its distance from this point. So h is representing the horizontal distance between these 2 points. Okay, and h can change. I can make h smaller if I want, okay? But h is the distance between these 2 points. Okay, so then once we have 2 points, we can draw a secant line between those, okay? Think back to geometry. A secant curve, or a secant line, is a line that intersects a curve. We learned it for circles, but it's a line that intersects a curve at 2 points, okay? So this is a secant line, all right? And now the idea is, as h decreases, this point will get closer and closer to the value of c, okay? And watch what happens to this secant line. Okay, whoops, it doesn't stop. Okay, let's see if I can stop it close here. As h gets very, 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 very small, then c plus h almost lands right on top of c, meaning that point Q is approaching point P. So we almost have 2 points that are in exactly the same spot. Okay, and so the idea is we start with the slope of the secant line, and hopefully you're thinking, that sounds a lot like we need a limit, okay? And that is what we need. So we are going to write the slope of the secant line, but then we're going to say, what if that second point moves towards the first point, and so that essentially the distance between them becomes 0. And if the distance between them approaches 0, now we have a limit, and the limit allows us to take the slope of a single point as opposed to 2 points. So going back to this is a big important idea here, that the slope of a tangent line is derived from the slope of the secant line, okay? And we know that the slope of a secant line is y2 minus y1 over x2 minus x1. Okay, now I'm going to draw a curve. Yours can look however you'd like. I'm just going to do something like this, and I'm going to say that my point P, my starting point here where x equals c, I'm going to put it right here. Okay, again, you can put yours somewhere different if you want. And we are trying to approximate the slope of this tangent line. Okay, and so to do that, we start with a second point. I'm really just redrawing what we had on the other screen here. Okay, so now really these 2 points are very, very, very close together, but just so that we can see what's going on, I'm adding some space between them. So this x value is c plus h, so h is the distance between these 2 points, and that gives me a second point here. Okay, and then our secant line is this, but then this point is moving closer and closer to this point P over here. Okay, now currently the slope between the two of the 2 points on the secant line, now my y2 is going to be the height at the second point, so that is f of c plus h, minus, and then y1 is the height of the first point, which is f of c. I mean, just using function notation here instead of y's and instead of y's, okay? And then divided by my x2, my second x coordinate is c plus h minus, and then the first x coordinate is point C. Okay? Now, we can simplify this denominator a little bit. Now, this is important, okay? Function notation, we cannot make this f of h. F of c plus h minus f of c is not f of h, okay? Those stay separate, so f of c plus h minus f of c is our numerator. Now c plus h minus c, we can cancel out those c's and we get an h. Okay, so this right here is the slope of the secant line. To turn this into the slope of a tangent line, we need h, the distance between the 2 points, to approach 0. So we stick a limit on it. Okay, so for the slope of the tangent line at x equals c, we have the limit as h approaches 0 of f of c plus h minus f of c all over h. Okay, and this, I rewrote that over here, but this right here is our definition of the derivative. Okay, and more specifically, let's add this on the right. Actually, I'm going to add this on the left. Okay, more specifically, move this over. This is f prime of c. Okay, so this definition is one that you are going to need to memorize. It's important that you understand where it comes from, that it comes from the slope of the secant line. Okay, but this is our limit definition of a derivative. Okay, so if I say if I say use the definition of the derivative, I'm not asking you to give me a sentence that says that the derivative is the slope of the tangent line. I'm asking you to use this limit to evaluate. Okay, so let's do a couple examples. For this first one, we have f of x equals 1 over x. First, we're going to sketch it just because it's nice to look at things visually, and we should know what that looks like. And then we're going to verbally describe what the slope is doing, and then use that information, use the definition to find the slope of the tangent line at x equals 4. So this will be our c value, and we will use this definition. Okay, so pause and sketch 1 over x. Okay, we should have something that looks like this. It's a hyperbola with asymptotes on the two axes, curves in quadrant 1 and quadrant 3. Okay, and at x equals 4, let me make this a little bit longer. Okay, we'll say 4 is somewhere right around here. We are looking for the slope of the tangent line right there. Okay, so describing this slope, pause, write down a couple things about this slope, couple observations. Hopefully you said something like the slope is negative everywhere. Okay, so the slope, and therefore the derivative, is always negative. Okay, now I would not say the slope is always decreasing. The function is always decreasing, but the slope is not always decreasing. Okay, on this part of the curve right here, the slope is actually increasing because we have a very negative slope and then less negative, less negative, less negative. But over here, the slope does decrease. So we could say on negative infinity to 0, the slope decreases toward negative infinity. And then on 0 to infinity, the slope increases from negative infinity, I don't want to say to, so I'm going to say toward 0. It approaches a slope of 0. Now, it never actually reaches 0 because we have an asymptote there. Okay? All right, so part C, let's use the definition to find the slope of the tangent line at x equals 4. So 4 is our C value, and we are using this definition. So writing complete statements, because we need to do that. So f prime of 4 is equal to the limit as h approaches 0 of, now we can do this in 2 steps or 1 step. We can go ahead and write f of 4 plus h minus f of 4 all over h, and then plug those values into this function on the next turn, or on the next step, and I'm going to go ahead and do that since this is the notes. That way we know where things come from. So f of 4 plus h minus f of 4 all over h, okay? Or you can skip right to the second step, that's no big deal. Keeping the limit notation, because we haven't evaluated yet, so limit as h approaches 0. So f of 4 plus h is going to be 1 over 4 plus h, minus f of 4 is 1 over 4. All of this is over h. Okay, if I try direct substitution and I plug 0 in for h, I have 1 over 4 minus 1 over 4 all over 0. 0 over 0, remember, is indeterminate. That means we keep going. All right, and so now all that practice we got in the last unit comes in handy. To simplify this, to get rid of the inside fractions, I'm going to multiply on the top and bottom by the least common denominator, which is going to be 4 plus h times 4. 4 plus h times 4, okay, which will give me the limit as h approaches 0 of, okay, distributing this to this, the 4 plus h's cancel out, so I have 4 minus, and then 1/4 times this, the 4's cancel out, be very careful here. You need to keep this negative. So we can put 4 plus h in parentheses and then keep the subtraction in front. Or you could distribute and have 4 minus 4 minus h, but that sign's going to make a difference, okay? Over, nothing to cancel here, so we have h times 4 plus h times 4. And again, leave this factored because the idea is that we're going to try and cancel out the factor that gives us that 0 in the denominator, which is the h. All right, so then 4 minus 4 is 0. Those cancel. And so we have negative h, and then down here, the negative h will cancel with this, so we're going to cancel this out and have negative 1. So now we have limit as h approaches 0 of negative 1, because of that negative, onto the h, over 4 plus h times 4. Plug in 0 for h, we get negative 1 over 16. Okay. Now, let's check. We want to ask ourselves, does this answer make sense? Okay, negative 1/16, looking back here, does it make sense that the slope of this tangent line could be, oops, didn't mean to do that, could be negative 1/16? Yeah, it does, because we should have something that is negative, okay, a negative slope that is approaching 0. That is pretty close to 0. That's a very small negative number, so that does seem to make sense. Now, had we forgotten to distribute this negative, we would have a positive h and then a positive 1, and we'd have positive 1/16, which does not make sense with a decreasing function, okay? So you're going to hear me say this a lot of times, but don't let algebra be the reason that you don't do well in calculus.